All right, welcome to Monday. Hope you guys had a good weekend. I hope it wasn't spent, the entire time wasn't spent working on Comp 15 homework. Hope not. So today we're going to talk about a bunch of different things. The main part of the topic is going to be on these things called tries, which are otherwise known as prefix trees. And unfortunately, the name try is pronounced by some people tree and some people try. And we'll talk about why that is in a little bit. But we will call it them tries in here. All right. So let's see. Here's what we're going to do in a little more detail. We're going to talk about UNIX Tip of the day. Namely, we're going to talk about doing multiple commands on a single line, which is possible to do and might save you a little time if you're doing a lot of like recompiling. And then we'll talk about homework 3 a little bit more. I've got some comments that we'll go through in a little more detail. The next free block. That seems to be what's confusing some people or people are having trouble with it. So we'll talk about some different ways we can attack that. And then we'll talk about a couple other things with homework 3. So the midterm is next week. Nobody ever likes midterms, but the midterm's next week. I will go over a couple of kind of types of questions you can expect. So you can start studying if you want. And we'll talk about that for a few minutes. Then we'll talk about some operation complexity. In other words, some asymptotic complexity for the operations that we had in trees. We will follow that on by talking about these things called tries. Any questions before I get going? OK. So let's start out with the UNIX tip of the day. So one thing that I noticed when I have been sitting with a lot of people trying to debug their stuff, a lot of times you'll type stuff like you'll go, let's see, reset, and then you'll say make, and then you'll make it, and then you'll run the application and whatever, and hopefully you'll come out with something that looks vaguely like that. Well, hopefully you'll come out with something that's exactly like that in the end. But what you can do is you can actually combine commands on the command line. So you can type, for instance, you can type reset, and then instead of typing enter and waiting for it to reset, you can type ampersand ampersand, which says if the previous command does not fail, reset's not going to fail, but if it was make or something, it might fail. If it does not fail, do the next command. So then you could type make, and then you could type, say, another ampersand ampersand, and say, run your calendar program, right? All one word. What it does, it resets the screen, it runs make, and then it runs the actual application. It does it all like that, right? If there was a mistake in one of your, like in your program, so let's say I had main and I had, this homework stinks, something like that, right? And it was on my first line, and of course that's not going to compile because the homework doesn't stink, of course. But anyway. You would run it like this, and what would happen is it would go ahead and do the compilation and then say, hey, I got all these errors, right? And it would not go and try to run the program. That's what the ampersand ampersand means. OK, so it might save you a little bit of time. Instead of retyping everything every time, you just type it once, and it does all of your stuff all at once. OK, questions on that? Not the biggest. Another hint that I've got to do at some point is this idea of piping commands, which means sending one command to another to another. We've done a little bit of that before, but we should talk more about that in detail because it's actually one of the what do you call it? One of the power applications that Unix came with in like 1977 or whatever Unix was designed. This idea that you could take a little program that does like one thing, take the output of that program, stick it into the input of another program that does something else, and then do the same thing along the line. And you can get lots of different functionality out of it. So little pieces that add up to one bigger piece. So we'll talk about that in a little bit. Questions on the UNIX tip of the day? OK. All right. All right, homework 3. So this next free block thing. All right, I know that's kind of been bugging some people about how to go about doing this. Remember what next free block actually returns. It just returns an integer that says the time of the next free block that will fit your event that happens to be at or after the event when it was requested. Right? That's what makes sense for that thing. Now let's say you had a number of events here. say event 1, event 2, event 3, something like that. And you're trying to stick an event in there. There's a couple cases, like there's some special cases you're going to have to deal with here, right? Like for instance, if you tried to put an event, your event, new event or something, in and it was before the first event, you could just stick it right there, right? Like that's where it would fit right there. If it fits right there and doesn't conflict with the first one, you can put it there. So you could treat that as a special case, right? You could just say, hey, if it doesn't conflict with the first one, stick it right there. What if it does conflict with the first one? Like then we've got this case where you're going to have to go down and figure something out. So what if it was like right there? What would you do in this like to try to like figure out where it's going to go? What are some ideas? There are numerous ways you can do this. But what are some ideas? Something that you guys thought about? Lydia?
I would like reset. Like I had like a working variable for the start and then time, and I would change them to like the end of the first event, and then like add on. You had like a duration function, so I would add on the duration of the event and have it end after like a new duration, so I would do end time and then check it.
Yeah. So basically, you're saying if these two conflict, you're going to take this event and you're going to kind of reset it to be at the end of this first event. That makes sense? Yeah, I like that idea, right? So then we could have this event, and we just actually reset we figure out the new start time and the new end time to be at the end of this one, right? And now you can now say what? You could then check it against this one. If it doesn't conflict with event 2, what do we know about it? Can it go right there? Yeah, so that's actually one good way to do about it. Once you can check the first one, and if it does conflict, reset the event so that it starts at the end of that one and ends at the appropriate time, and then check it against the next one, and just keep doing that, walking this event down until it actually fits. So if it did fit, it goes there. If it does conflict with this one, redo this whole thing. Start it right there, and then check against the next one, etc. Okay, so you can do it that way. I did something similar to this. I actually made it real simple on myself. I just said, I'm not going to do any of those special cases. I'm just going to start out and say, does it conflict with anything in here? And as I go along, do that updating, right? And then at the end, well, I know that I have a free block, like a time that works, or I have a situation where it's going to be at the end of the day and it doesn't actually fit. Right? So that might be that's kind of the way I thought about it. I said, I'm not too worried about going through the whole list. It might not be the most efficient thing in the world, but if I go through the whole list, then I can put the event in at the end of that. I know I'm going to have a free block that's available at the end, if not somewhere else. Okay? Anybody have any other ideas about that? Like that's the logic about it, right? Is that what you're going to same sort of thing? Okay, yeah. I mean, that's kind of the logic on how to do it. The devil, of course, is in the details and like getting it to work right. But you don't necessarily have to have a whole bunch of different cases, like at the beginning and the end and whatever. There's not quite as many cases as some of you guys were trying to do. Question, Margaret?
Don't you need to make sure that you don't accidentally schedule an event before start time?
You do, actually. Yeah. So that would be another like special case. The first thing you'd probably do is you'd go through and find the first event that might have a start time that is what? Before the end time of this, I guess, something like that, and then you could check, and then you would have to check it. So yeah, that one is a special case too. Good point. Yeah. Anything else on that? So there's a couple other things I noticed some people doing that involve pointers, and I get a little bit like sad about this because pointers are like hard. They're hard to teach. They're hard to understand for the first like million times you do them, and they're just kind of they're tricky things. And then I see people making mistakes, and it doesn't surprise me. It just makes me a little sad that happens. For instance, in I think is it schedule? Is it insert new day? I forget which one it is that returns the day. It's insert day or whatever it is, insert new day, something like that. It returns a day that you can then schedule an event into, right? Well, it's returning a pointer, right? You can do the following. You can return your day list, actually not quite like this, day list say 3 or whatever it ends up being. You can return the pointer to that day list event, right? Like that's how you'd have to return that actual, that one. A lot of people are setting up a temporary day, something like, up far they say something like temp equals, I forget what it is exactly, but something like day, and they're putting the details in there. That's fine. And then at some point you have to say like day list I equals star temp, or if it's not a pointer, you'd just be temp or something like that. That statement is saying copy everything from temp into your day list. Like actually go ahead and copy everything in there, right? And I wrote a copy constructor and an operator equals overload constructor, or operator equals overload function that actually does that properly for you. So if you do that, it should work. Okay? What happens then is that if you do this return, you're fine. If you return this, if you try to return temp, which a lot of people were doing, right? It is a pointer. It is to the day you just created. The problem is it won't propagate through properly later. Like you'll change stuff in whatever you pass down here, and then eventually that'll get destroyed or whatever. And in fact, it would if you did it like this, it would get destroyed right at the end, and you'd probably segfault, but maybe not. It's a thing. So don't do this, right? Make sure you're returning the actual day list itself, pointer to the day list object itself. Okay, I saw a lot of people doing that you got to be careful with. Okay. The other one that people seem to have trouble with was the conversion to 24-hour time, or from 24-hour time to like 12:30 p.m. or whatever. That's a little tricky. It does involve strings. If you're still having trouble with it, come on into office hours and or email me and we'll figure it out. That one shouldn't be I didn't mean for that one to be the hardest part of the assignment. Okay. Any questions on homework 3 at this point? No? Okay. Do come to office hours if you do have some other questions. Okay. Let's move on then. So the midterm. So full of good news today, right? So the midterm, March 12th. You are allowed, just like you were in Comp 11 if you took that. I'm not sure if you guys had anything in Comp 50 if you were allowed anything, but you are allowed to one page back in front, handwritten note sheet. I always figured that the benefit of the note sheet is actually in writing it. Like, I mean, you get the most benefit out of like sitting down and putting it all down because it means you're reviewing it. Like you don't actually look at it too much during the actual test. Sometimes you do, especially if you're in panic mode. At least in my experience. But you are allowed that. I will not collect it, so don't worry about whatever. I might come around and take a look. I don't even think I'll do that, but please don't type it or have it like micro font or something like that. But writing it out is the important part. And there will be some questions on big O notation. I'll go over an example of that in a couple minutes, so you'll kind of know what sorts of things to expect. You'll have to write a little bit of code. I don't expect you to write tons of code, and I'm not going to trick you. I'm not going to say, here's some obscure C++ syntax that, well, you guys might think all syntax is obscure, but I'm going to try not to like trick you by syntax, right? And we're not going to be grading on syntax. We're going to be grading on, like actually getting the logic correct. That's kind of the big thing. You'll have to find some bugs in the code. For those of you who were in the lab earlier, did you find any bugs in that code in the lab? Yeah, so the lab this week is all about finding bugs in assignment 2's code. So there are some properly anonymized assignment 2 results from your homeworks that some people didn't get the right answers for, like for instance, not canceling events properly or whatever. And you have to go through the code and look at it and try to figure out where it is. And you do it with a partner, and it hopefully goes pretty well. But that's in the lab. So you'll have to do some of that, not big, huge chunks of code, but little chunks of code. And you have to figure out what's wrong with it, because that's a pretty good skill. Okay. We are going to have a good review class March 10th. I say good. We're going to have a full review class March 10th. On review, we'll go over problems types and that sort of thing, and kind of do a basic review of what we've covered so far. And I actually have to be in Seattle for the Navy this weekend, so I'm taking the red eye back on Sunday, so I may be like this when we get to class, but I'll try to do all right. And that'll be on Monday. Okay. Yes. Go ahead, and then Margaret. Yep.
Will we be able to take the exam in the 10:30 class?
If you want to take it in the 10:30 class, I'm happy for that. Yeah, that's fine. You take whichever. I hope we have enough room. That's the only thing. Is that your other question?
That was the question. So it's during class.
During class, yeah. Yeah, in here. Unless, yeah, in here. I suppose you'd be the first one to get kicked out if the entire place was packed. But that would tell me how many people are watching the videos, too. But we'll see. Any other questions before I show you a couple practice problems? No? OK. So take a look at the following. So here's some code. OK. This was from a previous midterm. And it says to compute exponents, we can use repeated multiplication. Here's a simple function to do that for integers a and b both greater than or equal to 0. Again, I'm not trying to trick you. I'm not trying to like say, what's the problem with this? Oh, a could be less than 0 and it wouldn't work, blah, blah, blah. No, that's not what I'm trying to do. Integer exp1 int a int b, compute a raised to b by repeated multiplication. Z equals 1, y equals 0, while blank. Guess what you're going to have to do? Fill that in. Z equals z times a, y equals y plus 1, return z. OK? I'll give you a second to stare at that. The first question, this is like a four-part, small part question. Question number 1 is, what goes in the while part? OK? So a couple people have it already, I'm sure, but take a look at it. I'll give you a minute or so to figure that out. Any ideas? Dylan has one. What do you think?
While y is less than b.
Well, y is less than b, because the very good. Did everybody, or did you get that? If you didn't, that's all right. You'll have time to like concentrate on it. While y is less than, while y is less than b. OK. Question A was what goes in there. Question B is what was your logic in figuring out that that was y? It was y is less than b. You want to give it a shot?
Sure. So you multiply some number times itself as many times as there is a power, and if y starts at 0, you'd want to have some sort of iteration every time you go through, and the code looks like y would be that iteration variable.
Sure. Looks like y would be that iteration variable, and you're counting up. And how do you know that it's y less than b?
Because you're raising a to b, and so a is the number that you're multiplying by itself, and b is the number of times you multiply by.
B is the number of times you multiply by. Good. OK, so you don't have to, that would be plenty. That would be, in fact, probably too much writing. A sentence or so is good. Yeah, Margaret?
So shouldn't y be equal to b then?
If y equals b and starts at 0, have you gone enough times? Too few or too many? You got to walk through the code in this case to see. So let's say you were doing a raised to the 2 power, right? And y starts at 0, while y is, and b is going to be 2. How many times do you multiply a times itself if you're squaring it? Twice, right? So while y is less than b, because y goes from 0, and then it goes to 1, and then you're done. All right? So yeah, that kind of logic, you'll have time to think about that, think it through during the quiz or the test. Okay? All right, good. So that's a question. Let's see. What are some of the other questions I'm going to ask for this? Here we go. So explain. So we did the first two. Explain number 3, or rather argue why it actually returns a to the b. Now, 2 and 3 are kind of similar, but 2 you don't need to explain that much. 3 you really have to say, hey, why is it actually a raised to the b power? And you kind of gave a little bit of that earlier, where you said, look, that means that you're multiplying a b times and going through this loop b times by doing y starting at 0, et cetera, et cetera. You will end up raising it to the power. And you could also say, and by the way, z is what's getting multiplied by a, and each time, and we're returning z. So that should be good. Now, the last one could scare you a little bit, because we haven't really talked too much about this. But you say, what is the running time of the function exp1 as a function of a and b, one function of a and b, in big O notation? How might we go about thinking about this? Like, if we're trying to figure out a and b, what do you think? Phoebe, what do you think? Yeah, did you have your hand up? Oh, OK. Think about it for a sec. Like, what kind of analysis do we need to do to figure out what the big O notation is on this? Yeah.
In the loop, you're doing multiplication b times.
So you're saying in the loop you're doing multiplication b times. So basically you're saying, hey, we need to analyze this kind of instruction by instruction a little bit, right? I mean, in some sense, we probably want to, right? By the way, what is the running time as a function of a and b? F of a, b equals something, right? That's a function of a and b, which equals big O of something, right? So this is what I'd really expect you to start thinking about. Now, as you go through this, the analysis we did the other day works pretty well. We're going to end up ignoring some of the things, but we might as well go through this kind of one step at a time and to see what each expression does. Did you have a question, Allison? No, OK. All right, so take a look at, for instance, how many what did we call them, primitive operations does int z equal to 1 equal? I'm hearing some 1s and some 2s. I don't really care. It's not actually going to matter that much, right? In fact, it's not going to matter at all. But let's say, I might say, int z equals 1 is probably two primitive operations. Why? Because you're creating an integer and you're setting the number equal to that. So let's say 2. So I would start counting and say, all right, there's 2 right there for the first statement. What about int y equals 0? Also 2. OK. All right, let's keep going down while. OK, now this while loop, you've got a bunch of stuff going on in here. We already said that inside the while loop, there's going to be a comparison, right? Y is less than b. How many times does that comparison get generated? Yeah? Well, just what's in the while loop. How about that one? Yeah, it's actually like I think it's exactly b times. It might be b plus 1. I'm not going to worry about that. Let's just say that it's one operation for inside the while loop, and then z equals z times a. How many operations is that? 2. OK, and then y equals y plus 1. Also 2. So really 4. So 5 total. I like that, right? So 5 times how many times are we doing that inside loop? B times, because we're going through that. OK, and then we're done with the while loop, and then what? One more extra there, right? Because the return is just, we're saying return is one operation. We know return's not one operation. Return does a whole bunch of stuff. It pops the stack, and it moves variables around, and it has to jump somewhere. I mean, it's a bunch of stuff. But really, we're just not going to care. We're going to say it's one operation. OK, so when we add all this up, what do we have? 2, 2, 4. So we have about 5b plus 5, something like that. I mean, if you were off by 1 here or here, it's actually not going to matter. Is a in there at all? Does it matter what a is? No, actually, right? Because you're taking a times whatever. A is just a number, and you're multiplying it by some other number that's doing the looping. So yeah, it doesn't matter. How do we reduce this into our big O notation? Get rid of some constants? That one's definitely not going to matter, because that's just adding 1. That's just like the overhead cost. And then this one, we don't care about that. If it's 5b or b, it's in the long term, it's really just not going to matter. So there's your big O notation. OK? Not too bad. I mean, you had to do a little analysis, but it wasn't too bad. Right? And that's it. And again, if you said it was 6b plus 5 or 5b plus 6, I'm not going to take any points off for that. Right? The real answer is order b, but getting there is kind of the important part. Questions on that? Yes?
So on the test, we're going to have to write the 5b plus 5?
Yeah, I mean, I would expect you to do that. I would expect you to show the kind of how you got there. But I'm not going to take points off if it's 5 or 6 or 4 or whatever. The real answer is here. But this is just, hey, what was your thought pattern? I mean, if you all of a sudden had like a, 3a plus 5, I mean, wrong, right? If you all of a sudden had something like that, then I'd start taking points off. But otherwise, you wouldn't lose me on the details there, because again, this return statement is not really 1. It's more like 12 or something. I mean, so it doesn't really matter in that sense. OK? Any other questions on that one? Yes?
Do we call that like a linear function?
This is definitely a linear function, and it's linear with respect to which variable? B, right? I mean, B is the one that matters. B is the n in this case. And if you had said all of this and said order n, that probably would be a point off, because it's not order n in this case. You'd have to define what n is. I mean, you'd have to say so order n, n equals b, or the number of how many times b is, something like that. You'd have to be a little more explicit. But if you're going to do a function of a and b, it should be in terms of those two variables. in the end, okay, if necessary. Might not actually, if there hadn't been a while loop at all, right, it would have been just constant time, 1, or whatever. Okay? Questions on that? That's good. All right, let's see what I had for the answers here. So what statement-wise? Lesson B, explain how you describe it. We need the loop to stop computing when y reaches b. I mean, that's about all you really need for that. Y, xb1 returns a, z is multiplied by a number of times equal to the number of times through the loop. Because the loop is executed b times, then z will equal a times da. Nothing too extensive. Explain it like, explain it to me as if I didn't know that much algebra. Okay? All right, and then finally, what's the running time? Let's see, what did I have? 5b plus 3. So I probably only counted int z equals 1 to 1 as one operation and return as 1. Yeah, so no big deal. Okay. All right, take a look at this one. It's another problem. By the way, we'll do kind of similar things like this on Monday, too. We'll have some other kind of questions. Following is a recursive implementation of a function to search for a value in a linked list. Okay? And I am not going to try to trick you, like put a little 1 colon there and say, what's the problem with this, right? No, that's not the important part. Okay, explain 2 things that are incorrect in search. Will any of the problems cause a compiler warning or compiler errors? We'll take a look at that. I'll give you a minute or so to think about that. A couple people have some kind of, back there.
When you call search again, you're passing it not a pointer because you're dereferencing next.
When you call search, you're passing it a, no, actually you are passing it next, as long as next is a pointer, which it is, right? It points to, as long as next is also a pointer, that's okay. Good idea, though. Yeah?
It's going to return false 100% of the time.
It's going to return false. I don't believe that it will return false 100% of the time, but you're close. What's it going? It may not return false 100% of the time, but what will it do?
It's just not going to return true.
It's just not going to return anything after that search function returns, right? Because there's no return function. Will that cause a compiler warning or error? Yeah.
The warning where it's like, there's a case where this doesn't return.
Right. There's a case where this doesn't return, or what is it?
Not ending.
Yeah, the function ends without returning a value or something like that. Yeah, I think that's a warning, but it may in some instances actually not produce an executable. Yeah, that's good. Let's see. What is the other case here? There's one other mistake here that I haven't heard yet. Yeah, Lydia.
What do you like? It doesn't look like it's. I don't know. I'm not sure about this, but it looks like it's not really doing anything.
Looks like it's not doing anything. Yeah. Where does it look? Where should it be looking for something? Right? Like, did it ever compare anything besides null to that pointer? Yeah, it's never actually comparing the search to anything, right? So that's another issue. Will that cause a compiler warning or an error? No, that won't. That's like saying, hey, I'm doing everything right, but the computer has no idea what you're trying to do, right? I mean, except for the return part. If you had put return search find it pointer next, then you would actually return false 100% of the time, and it would compile fine, and you'd spend 4 hours talking to TAs in the lab and trying to debug it, right? Hopefully not, but that's kind of that would be fine. Those are harder errors to actually debug. Okay, yeah, good. Anything else on this one? I think there are only 2 in that one that were problems. Okay. All right. So any other? Yes. The second one, does it ever compare like what you're supposed to find it to anything in the node, like the actual value of the answer? It doesn't actually do any comparisons there. The only thing it compares is if the pointer itself is null. It never compares the find it to the actual term or the actual value it's looking for. Yeah. So not such a good function here. Okay. Anything else? Okay. All right. So let's go back a minute and talk about binary search tree complexity. We kind of keep talking about, binary search trees, they're great. They're all log n and blah, blah, blah. let's dig a little bit deeper and figure out what some of the complexities are for these things. We got to remember, of course, what we actually did to do these, to actually to run these operations on a binary search tree. But what did we do to do find min? What did we have to do in the binary search tree to find the minimum? Allison?
Just went all the way to the left.
Went all the way to the left. OK, so this is my binary search tree. 1, 2, 3, 4. Is that a binary search tree? Yeah, it is. It actually works. It's not a very good one. Like, it's not particularly good. But OK, so you go all the way to the left. If I was to search for min here, if I was to do find min in this, what would the complexity be of this tree? Yeah? Oh, 1. Yeah, it would take one comparison, basically, to find the minimum there. Is that true for all binary search trees? No. What if I had this binary search tree? 4, 3, 2, 1. What's the complexity there? Order what? Order 4, or in terms of if that was n number of nodes, what's the order of the complexity there? Order n. Do we have our minimum case and our maximum case? Yeah, or our worst case and our best case and our worst case. Yeah. So for a binary search tree, remember that horrible binary search tree, both of those are actually just linked lists in this case. So for a binary search tree that doesn't have any special properties like that it's somewhat balanced or whatever, you've got a best case of O1, which is great. Worst case of ON. We always really care about the worst cases. So binary search trees aren't necessarily looking so great right now. On average, I'm not going to make you figure these out, but on average, it's actually the square root of n for a regular old binary search tree. O square root of n. You know, if you just had a regular binary search tree and just were inserting, you know, random numbers, it would be the square root of n, as it turns out. But again, we don't really care. We know now that the worst case for find min in a binary search tree is order n. Not so great. Order n is not terrible, but it's not this great log n that we've always been talking about. Max is going to be exactly the same. How about contains? Contains, remember how contains works? Who can remind me how contains works in a binary search tree? If I had a binary search tree that was slightly better, and it was like 4, 5, let's see, that's not going to work. 5, we'll call 3 here, and this one, 2, whatever, right? That binary search tree, right? How do we actually find the value 3 in it? You answered already. Somebody else hasn't answered in a few minutes. How do we find the 3? Yeah. Yeah, you check and set right, exactly. You check the node you're at, and you say, is this one equal to 3? No. Then you go with one way or the other, depending on our condition that says everything to the left has got to be less. So, or everything to the right's got to be more. So we go here, do the same check. OK, for a binary search tree, what is the best case scenario for contains? 1. What's the best case scenario, or sorry, the worst case scenario for contains? Also order n. Not looking so great. Insert. What's the first thing you have to do when you do insert? Compare it. You have to find, right? Basically, the first thing you do is contains. Can insert be any better than on? Order n. Nope. Insert's going to be remove. What's the first thing you have to do when you do remove? Compare and find it. Same thing, right? So even remove is going to have trouble doing that, right? Is remove worse than order n? Remove, remember what remove does. It goes down and finds the node, and then it has to make that decision. It has to say, OK, if it was, let's see, if I have no nodes, I just remove it. Or if I have no children, I remove it. If I have one child, I can actually remove that one, or I can bypass it. If I have 2 children, then I have to do this. I have to figure out the lowest of the. Can it be worse than ON? Well, it can be order n plus something, right? Like it could be order n plus, I don't know, like 6 or something, because it's got to find all those other nodes, right? Is that going to be any different than order n in the asymptotic case? No. So we're still going to say, even though there's some extra stuff to do with remove is also order n. OK. So we've gone through all these things. We found for a generic binary tree, not really so great in the worst case. Average case, good. Worst case, not as good as we'd like it. All right. The AVL tree. Remember, the AVL tree is relatively balanced. Okay, relatively balanced. Does that change any of the complexity of those operations? If we are trying to do find min in an AVL tree, you still have to go all the way left, correct? For finding min in an AVL tree. It's just a binary search tree that happens to have this property of being balanced, right, more or less. What would the complexity be of an AVL tree doing find min? James? Log of n, right? Because it could be log of n plus 1, right? Because it might not be balanced on this side. Like this one's not as balanced as that one. So maybe it's a little bit more. But that plus 1 doesn't matter in the asymptotic case. Does not matter, right? So for an AVL tree, right, we've got order log n for find min and find max. How about search in a binary or contains in an AVL tree? Same, right? It's going to be the same. Because why is it going to be the same? Because it's the same idea. You only have to go down the logarithmic or the logarithm of the total number of nodes because it's balanced. Awesome. OK? Or order log n. How about, let's see, we've got insert. Now insert for an AVL tree. You have to go down there and you insert it. And then you have to make that decision about rotating. And you could do a double rotation or a single rotation or all that. Is that going to change the overall order of this? I'm seeing some heads shake no. Why no? Yeah, why no? Yeah, you're only adding a certain number of operations. Remember, the rotating does not take many operations. I mean, it takes a few, and you definitely have to do it. If you're talking about a million node tree, doing 10 or 20 operations more to do the balancing, not going to make a difference, right? So it's still going to be log n all the way, even for insert an AVL tree, which is interesting. If you're like the fact that you can keep a tree balanced by a constant number of operations is a pretty cool thing. Like the complexity of the balancing is 1, really. So that's kind of a cool thing in terms of the AVL tree. OK, so basically AVL trees, good. They give us the log n that we've all been talking about for binary trees. That's what we're looking for. OK, questions on that complexity? I know there was some hand waving in there, but that's what a lot of this order n stuff does. Somebody was telling me, I forget if you were in here, telling me about taking discrete math right now, where you're doing this same sort of thing. Anybody taking discrete math right now? Yeah, do you do an order n? Yeah, you're doing like order theta and order like big little o and all that kind of. We're not going to worry about that right now. You can worry about discrete math and then in algorithms. Don't worry about all that. You'll get there if you take the other classes. OK, so those are the complexities there. Now, we are going to talk about another kind of data structure, OK, called a trie. OK, I mentioned earlier that the name is somewhat unfortunate. So it stands for retrieval, T-R-I-E, in retrieval. And the guy who created this data structure calls them trees. But we already have a name for trees, and it's spelled different, right? This happens to be a tree, but is a certain type of tree called a prefix tree. And we'll get to see what that prefix part means in a few minutes. I am just going to call it a trie. Okay? You can call it whatever you want, but make sure if you do call it a tree, you explain what you mean. Okay? What might a balanced binary search tree look like if we used words instead of letters? Okay? Actually, I don't think I need this. If you used words instead of letters, okay, in a binary search tree, it might look like the following. Okay? I grabbed these words from like a 3rd grade word list. Just so you know, my nephew's word list. The following words, if we were to put them in a binary search tree by word, you can compare words alphabetically, right? If you look at cow, it is farther up in the alphabet than fire, which is farther up in the alphabet than red. Right? This would be a binary search tree, and it would be legitimate. And we can write a comparison function to compare words. In fact, strings, you can already do that. They kind of screw up in things where you might not expect them to, like if there's like, let's see, what's a good example? I don't know, file names, like file 10. Now, this isn't strictly alphabetic, but file 10 actually comes before file 1. Right? And the problem is that it's like it's got to decide what it means to have different length strings too and all that. But we're not going to worry about that. We're just going to worry about letters. And in fact, we're just going to worry about lowercase letters. And in fact, we're only going to worry about lowercase letters in the Latin alphabet, which doesn't include crazy things like accents and all that. OK? Lots of like requirements here. But for now, this is what it looks like. So if we took this word list, OK? We know we can search in log base 2 of n. We just showed that for a balanced tree. It's definitely searchable in log base 2 of n. But we still have a worst case if it's not a balanced tree of log of order n. If it is balanced, we're going to get that order log base 2. But it turns out, and you can kind of tell that there's lots of words, especially in a dictionary, that actually share prefixes. Like the first part of the word is shared between a lot of words. For instance, cow and corn, right? They both share the CO. Okay, the prefix of cow and corn that's shared is CO. Okay, pit and pits has 3 letters over that actually get shared, the prefix of all those. Okay, that actually becomes kind of important and kind of cool when it actually comes down to it. What we can say is that these prefixes make it so that we can probably do better than order log n. Okay? Why limit ourselves to a binary tree? We did talk about this. Like, why did we pick a binary tree versus a tree that has like lots of different children nodes? What were our reasons for that? Anybody remember that? Yeah, Richard.
There's a clear rule, and otherwise it's tough to organize it properly so that you search it efficiently.
There's a clear rule. It's tough to search it efficiently. So searching it efficiently, if we made a ternary tree, right, you could probably search that relatively efficiently. You would have to make a decision about like what's greater than that. You would have to make one more case than if it's just greater than or less than, for instance. But you could search it. But I like where you're going with that. What happens if I wanted a tree that has unlimited types of numbers of children? What was the problem with that? Unlimited numbers of children. Yeah.
At some point, it kind of turns into a list again.
At some point it turns into a list. And in fact, it is a list. B, if you don't know how many nodes there are going to be, you've got to figure out how to take that into consideration. Now, you can create a linked list, and it'll just be however many. And you can do that. If you wanted to do it with an array, which is generally faster, you're going to have trouble because you don't know how many. You'd always be expanding it. And so it's just kind of painful. All right. If, though, we were able to do this in a ternary tree, we would actually be breaking it into 3, like each level would get broken into 3 different sections instead of 2, and we would be able to get log base 3 of n, which is faster than log base 2 of n. So there is some benefit to doing that. Okay, there is some benefit to doing that. What if, all right, well, we talked about this. What do we know about words? We already talked about this as far as the prefixes go. How many letters are we going to have to worry about? 26 letters. That's not too bad. If we're worried about if we only have to worry about 26 letters, do we know the maximum fan out, as they say, that we're going to have, number of children nodes? Yeah, we do. We're going to have 26. You could do that, right? We know that words have letters in them that are a fixed number of letters. Again, we're not going to worry about those other cases like digits and uppercase and all that, punctuation. But for now, we'll think about just 26. If there's a maximum of 26 children per node, we can do the following. Okay, we can actually build a better tree that's based on the prefix. Let me show you what I mean. There it is. If we break down our word into letters, and we say that the letters are going to, if there's, for every node, you can have up to 26 children, then as we go down words, well, you go from one word or from one letter to the next letter, and then when you get to a word that branches out, you just create the branches like this. Okay? There could be upwards of 26 possible children. Okay? There aren't too many words that start with, like, I don't know, C-O-Z or whatever, C-O, I don't know, whatever. But there aren't that many words, so you're probably not going to get 26. C-O is probably not a bad example. You could probably find C-O something for all 26 letters. But anyway, you're probably not going to get that. But this is how we're going to break it down. Now, notice something about this. A, we've actually saved some space in the sense that cow and corn, instead of taking a full node for each word, right, they actually share the first two nodes here and then branch off. Now, there are actually more nodes instead of just two. That is true, because we're just using one letter. But there is some compression thing going on here. Okay? Everybody get that? Get kind of what's going on there? Yeah? Good question. What's the root of the entire tree? We're just going to make it not pointing to any letter. Just it's going to be the root, and it's going to have 26 children, possibly, and that's all we're going to go with. Good question. OK. So if we take the same words that we had before, and we stick them in this tree, and there's your root with no letter on it. Those same words, fire, cow, red, pit, corn, sand, day, snow, pits, and fish, go in like this, right? You can still order them left to right, okay, in terms of the alphabetic nature of them. And as you go down, what you have to do is you have to mark where words end. Because, for instance, fi is not a word, right? FIR happens to be, but it's not in our dictionary yet. But fi is not a word in this case. It might be. I don't know. You guys play Scrabble? They have all those two-letter words that I don't think are really words. I think that's kind of cheating, but whatever. Scrabble dictionary, the Scrabble Association of the World can, I don't know, can deal with it. I guess I can. Anyway, you have to know where the words end. Okay, how do you know where a word ends? Well, part of your word ends. Part of your node says, is this the end of a word? And there's only one path to get to fish, for instance, F-I-S-H, and that H is the end of a word, and the word happens to be fish. Aha. Now, at this point, you might be saying, what's the point of all this? It still looks like a huge tree, and there's tons of nodes, and yeah, all right, it looks kind of nice that everything breaks up and you got prefixes, but what's the big deal? Well, here's the big deal. First of all, the cost of looking up a word is now fixed. What is it fixed by? If you want to look up the word fish, right, what's the maximum number of, maximum depth you have to go? 4, which is, well, or 5. I guess 5 if you're saying go 1 and then see if its next node is null. So yeah, but 4 or 5 anyway. But we'll just say 4 in this case. It's fixed by the length of the word that you're searching for, not what? The number of words. The size of your dictionary could be 1 billion words. If the size of your dictionary is 1 billion words, to find fish, you need to make at most 4 comparisons. Maybe 5, depending on how you're counting. Right? That is kind of a cool benefit of this try. Okay, it's definitely a cool benefit. No more need to worry about the length of the actual, or the number of words in the dictionary. Okay? Not based on the size of the vocabulary. You don't even have to balance this. If you had words and the longest word was supercalifragilisticexpialidocious, right? Well, sure, that one's going to be all the way down. That's going to be the longest letter, and you have to look all the way down there to get to it, right? But if every other word is less than that, that is the maximum word depth you're ever going to have to go. Okay, it's just based on the word length that you are searching for. Pretty cool. Okay, what's the complexity then? If we have the complexity of a try in terms of our big O notation, does it involve n, the number of nodes now? For searching, I should say. The search complexity. What is it? What would it be? It's it's order of whatever the word length is that you're looking for. Right? which is dependent on which word you're looking for, of course. But that's the search complexity for a try. Not bad. Okay, and generally much less than some of the other ways. Again, log n is pretty good, but this is even better. This really, the word length, let's say the word length was 10. Oh, 10 really is what? Order what? We get rid of the constants. That 10 goes to a 1. Order 1, which is constant. So tries allow us to have constant time lookup for your words. Kind of cool. Now, you might say, when am I ever going to do word searches and things like that? Well, lots of times you'll end up doing word searches. Anybody who has a cell phone who's ever sent a text before, and I know every one of you has sent a text. Anybody never sent a text? Some people might not have. Yeah, a couple people, yeah. Sending a text, you know when you're like typing it in and you get down to like somewhere and it auto-fills the word in for you? It says, it starts to give you the suggestion of what word it thinks you're going to do. That is based on this sort of mentality. You're searching for a prefix and you're going down and you keep going down. If you were to start figuring out where that actually, figuring out what that suggestion is going to be involves a little bit more logic and artificial intelligence and stuff. Yeah?
If you're like searching through a word through a try,
Yeah.
you still have to like look through 26 different conditionals for each letter of that word.
Wouldn't you have to look through 26 different conditionals? It depends how you set up your try. Hold on that. In about 10 minutes, you'll see a solution to that, which is actually pretty cool, pretty neat. Okay? Yeah, you don't necessarily, it depends. If you keep them in an ordered state, no, you won't have to. You could do a binary sort of search on the letters or whatever. If you keep those 26 ordered, then you definitely don't have to. Because in fact, you know exactly where each one is. Right? If you did a linked list, different story. Yeah. Although you could keep an ordered linked list and so forth. OK, in this case, so let's say that you're on your phone and you're typing CO, right? It's probably not the case that your phone is going to say cow, right? Because there's lots of letters that start with words that start with C. I mean, unless you typed cow like a million times, right? Cow, 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 right? And then maybe it would start to, it's smart enough to say, hey, she's typed this a million times. She types cow all the time. We're going to suggest that it's probably cow. She wants to, right? So it's smart enough. It's all artificial intelligence, right? And then it's artificial intelligence backed up by a lot of statistics. Right? Trust me, your phone knows what's more likely for you to type, corn or cow. Again, bad example for such short words. But when you're getting down farther, right, either A, you'll get far enough that the only word left in the dictionary is the one that you're going to type, right? Or B, you get far enough so that statistically, there's a really good chance you're going to pick one of those words and your phone will suggest it to you. Okay, so again, don't underestimate the power of statistics in all this. People have looked through like zillions of texts and figure out what people type on there, right? So that's that. But anyway, there's really good benefits to using a try for this sort of thing. Okay? Complexity, order 1. Here's another thing. When we looked at the binary search tree for words, when we're doing the comparison between fire and cow, do we have to compare letter to letter? What do you think? Do we have to compare letter to letter when we do fire versus cow? How do you do it in your head? Why is cow farther up in the dictionary than fire? Yes? Compare the first letter. OK. What if it was cow versus corn? How many would you have to compare? You'd have to compare up to 3 different letters, right? And so yes, you have to actually compare letters. A lot of this happens in the background. Now, if you were to write your own comparison function, you would have to go through each letter individually. That's hidden in this sort of comparison. If you have a string function that compares words, well, it's doing that under the covers. So it's not really. We still have to do it. It's just hidden from us. So when we look at this, when we look at our comparisons for our letters here, yes, we have to compare every letter. But you did have to do that same thing for a binary search tree. It just was hidden. The letter comparison part was hidden. OK? All right. OK. What about the size of a try? All right. What about the size of a try in terms of the amount of space required? So first of all, we can compress tries in the sense that cow and corn, like I said this earlier, cow and corn share those two letters, so those two words get kind of compressed right in there. Okay? And this is especially true for sources of data that have lots of these overlapping prefixes, like the English language, right? I'm not so sure about other languages, like languages that use characters as words, like a Chinese sort of language. That's a little different. I mean, it's harder to. I don't know if anybody. Do you even have alphabetic comparisons?
They store, because Chinese letters have to be written in a certain series of strokes.
Ah, okay.
So they store each type of stroke.
Chinese letters are stored in different types of strokes. If you compare two Chinese words, can you get an alphabetic sort of comparison, like by the strokes? I don't even know.
Basically, the modern system breaks down all the possible strokes to 9 different types.
9 types of stroke. Okay.
So
Oh, okay.
you can sort of like,
So if you did a try with Chinese characters, you might have 9 instead of 26 sort of things. Okay, interesting. Interesting. Does that make sense? Maybe.
Usually, you can sort of do a transliteration.
You can do a transliteration, yeah.
Modernization is just
Ah, okay. That makes sense. Well, anyway, it's different. It's more difficult when we get into and by the way, as I said earlier, we're not dealing with uppercase letters. We're not dealing with non-Latin letters with accents and things like that. We're not dealing with other languages. I mean, the model breaks down a little bit when you're trying to do that. There's a thing called Unicode, which is kind of replacing just the regular characters, which has all this configured into it. And smarter people than me have figured all this out, but that's that. Now, let's see, what else? They do take a fair amount of space in general because of the fact that you've got to keep all those pointers. If it's a linked list, you're not going to have to keep as many. If you're keeping an array, which would be very, very fast, you would keep kind of 26 pointers for every character, and that's a lot of extra space. So you get compression, but you also get some of the expansion. It normally doesn't actually take up less space than a binary search tree. It just is faster. Okay. All right. Now, let's see. I went and looked up try animations online, and there's a couple that I could find. I couldn't actually find any that worked. Right? The cool site that we used last week didn't have any cool try animations. And then the one that I did find wasn't working. Something was wrong with Java or something like that. So when you're faced with this sort of situation, you have to build your own. So I ended up building my own little try animation thing. And it's not perfect, but it's all right. Let's see. What were the words let's go back up and figure out the words that we need to put in here. There they are right there, but they are, hang on. Oop. There we go. Fire, cow, red, pit. OK, so we put fire in here like this, right? There we go. There's your try. OK, and it's just straight down. No need to worry about that. And the red letter denotes the end of a word. OK, fire, cow, red, and pit. All right, cow. There we go. Right now you've got a try that kind of branches off. All right, red. Red goes another one. I haven't actually come up with any words that don't branch at the first comparison there. Pit and corn. Pit is the same thing. And then corn will actually branch that guy off. Right? OK. And then let's see. Corn, sand, day, snow, and pits. Sand, day. Oh, the other one's, hang on. Snow and pits. Snow. There's snow, so snow's going to add this one. And then pits is just going to add a little s here, right, and make both of them red, because that's the end of the words. OK, so there's your try that hopefully looks just like the one we did over here. Let's see. Let's see, format, there we go. Yeah, looks pretty good. OK, so yeah, question, Phoebe.
So for example, if I have a word that contains another word like fireman, so man should go to the right branch.
Let's see, fireman. What would happen with fireman? You think it would go fireman, F-I-R-E-M-A-N? Well, I don't know. Let's find out. Nope, it just goes right below it. Right? Why does it go below it? There's no branching necessary. Right? Now, if it was like furman, like somebody, I don't know, carries fir trees around or something, yeah, sure. Then it would actually branch at the letter that doesn't branch, right? But that's that one. Yeah.
If you put fires now, plural, you would get a branch.
Yeah. If we put fires, now you're going to get a branch right here, right? Because there's going to be a branch there, right? And there you go. Now, if you go too far down in the thing, it overlaps because I'm not that good at programming, right? But anyway, so now the question is, how do you actually search through these? Well, it's really easy. Okay, if you're going to search for the word cow, right? Well, let's see, cow. Boop, there we go. Okay, it actually searches. It goes, finds the C, finds the O, finds the W, found the word cow. Right? Okay. What if we were to search for the word fir, F-I-R? What would it do? It doesn't know that it's a word. It tries, but it says, I've gotten here, and then I look at the next one, and that's not a letter, and I've actually gone too far. Not a word. Fir is not a word yet. Okay, and we could certainly add it. We could say, oh, and this is what happens when you add words to your dictionary, right? It just adds adds extra words. And let's see, I put fir in, and now fir is red, and it would find it. Okay. Any questions on that one? That's how this works. It's pretty simple stuff when it comes down to actually searching. This little web page is online. If you look at the website, you can go and play around with it. The code in C++, this is actually written in JavaScript, but if you look at the C++ code is online as well, and you can look at that. It's basically the same. I found a really good version online, and I'm not going to rewrite it if it's a really good version. So I've rewritten it to actually use nodes that we've had before, but that's that. Okay? Any other questions on this? Yes. Colin.
So if you were to delete a word, like if you wanted to delete the word fire,
Yeah.
would it just like unmark the E as being red?
Yeah, if you were to delete fire, there's a couple different ways you could do it. In that case, yes, you would still have fireman, and you would still have fires in there. So yeah, it would unmark S as or the E as being a word. Yep. Yeah, it would be there's various ways of doing it. I mean, you could kind of mark where the end of the last branch is or something. I mean, there's various ways. For deleting, if you want to actually delete it, sure. If we were going to delete fireman, we would go down here, see that we have to keep up to the E, and then go down here and whatever. Okay? Yeah. Anything else on that? I can't delete here. I didn't write that. But yeah, that's what it would do. Okay. Good. All right, so let's see. We did that, did that, did that, did that, did that. We can compress tries a bit more, right? We can compress tries by saying, look, anywhere on a leaf that doesn't have any more branching, let's put the whole word that's the rest of the one word left in that node. You would have to do a little more work for it, like a little more figuring out of, oh, I got to keep a whole string here instead of nodes, and I'd have one that's like, last word or something like that, and it would do that, but it would take a little bit more work, but you could do it. You could compress it more this way. We can do even better than that. Anywhere there's a branch, like for instance between F and I in fire and fish, if that's a branch, there's no branching there. We could actually make it like that. Now you've got even more work to do. Especially if you look at pits, for instance, and that was, I guess, in the last one too. You have to have two stars there. You have to know that both the T and the S are both words. Pits and pit are words. And it's more work, right? You could still do this. You'd get the benefit. You'd still get most of the benefits of a try, but you'd have more work to do when you're actually looking at it. Okay? All right. So we talked about searching a try. And this question came up earlier. I forget who it was who asked. Yeah, this question came up earlier and said, "Hey, do you have to look through the list of all the different letters when you're trying to actually do the search?" Well, in this search, the search word function, notice the highlighted line there. It says node temp equals current find child, and it passes in the letter in the word that it's trying to find. Okay, so when you do S bracket I is the letter number of the letter in that string. Okay, it's just like an array-like in that sense. The find child part of the node, the find child function of the node, take a look at how much code I have to write for that. Is it going to be a lot or a little? I hear both, little and lot. Let's find out. It's like one line. Here's what actually works. Now, this is going to look strange. Okay, this is kind of a this is a little trick that's like a C trick, C++ trick, ASCII trick, which ASCII stands for the character set that we're using. Remember that we're just using lowercase letters, right? We're only using lowercase letters. And in fact, if I tried to put uppercase letters in my try, it would fail at this point anyway. I guess I should rebuild it to do uppercase letters too. But anyway, here's what's actually going on. I'm saying this weird thing here. Return the children part of the array that's at location C minus character A. Oh man, what does that actually mean? Well, turns out that characters, chars, are really just numbers. They're really just integers under the hood, right? They're integers from 0 to 256, as it turned out. Actually, it might be negative 128 to 128 for some reason, but I think it's 0 to 256 in most cases. I'm not 100% sure on that. But letters have a numeric representation. Okay? Turns out that if the C was the letter S, and again, you guys got the benefit of being in the second class. I screwed up earlier. I said I used C as in confuse people. Anyway, if C was the letter S, the ASCII number for S happens to be 115. The ASCII number for A happens to be 97. When you do 115 minus 97, you get 18. Any guesses as to where S falls in the alphabet if you start from 0? 18, right? So that's how you can actually, it's 19, but if you start from 0, it's 18, I believe. I think it is anyway. Well, it should be, if it's going to work like this. These ASCII letters, I actually have a little, I know it's nerdy, but I have a little app, or a little thing on my desktop here that shows what the ASCII characters are for all these things. If you look at A happens to be 97, and then S happens to be 115, right? So if we have A as being 97, anything A minus A would be 0, which would be, wouldn't you want to label your, or put your characters into the array from 0 to 25 or whatever, right? It's kind of like the, it's kind of like doing a code when you're a kid, like A equals 0 and B equals 1 and C equals 2 and whatever, right? Or whatever. Well, it's kind of the same sort of thing. In this case, if you do the character C minus A, you get a letter, you get an index into your array that is the index of the letter you're looking for. So that's how we do it very fast, to answer your question. That's how we do it really fast. We don't worry about searching through them all. We just say, hey, let's use a little trick here to do that. This would not work for other languages and blah, 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 and uppercase and all that. Just wanted to show you the little trick here. Yes?
Why did you subtract from A? Why can't you just keep, like, I mean, if A is 115, why don't you just keep it 115?
So we've got an array that goes from 0 to 26. If you try to do 115, it'd be off the array, right? We just need to back it up to where it fits in the array, A being 0. Yeah, good question. Any other questions on that? Good. OK, I will leave you with this. If you're old enough to know Star Wars, I mean, you know. Who doesn't know Star Wars, I guess? But anyway. OK, any other questions on tries or homework 3 or test midterm or anything like that? OK. I've given you 5 more minutes in your day to work on homework 3. See you guys later.